Yes.
Our lab calendar and the seminar calendar. So I think the email was sent in the wrong room too. Yeah, we came down. Presumably more people are coming.
Also great because prior to this he was working night shifts, so I would come in the day, come home, see it, and work the night shifts, and we would end up seeing. So it was much better. And so we'll see how that goes. But it is nice to be able to universally.
I want to
I can understand that. Well, I know you want to. I feel like we never see you guys anymore now. You're on the other side of the camera.
礼儀正しいですよ。
So we had a little confusion about that. One more minute.
Cool. So Steve, you gave this seminar to kick off this year?
Yeah, the first one in January. Hey, Chris.
Hey, Chris.
When this is over, I'm going to spirit him away after the groupies have finished with you. Where do we go after that? Do we take him to your office?
Sure, that'd be great.
Okay, now I can't get in. Do you have a secret telephone number I can call?
Yeah, I'm sure.
I only have so much hand.
Thanks, Chris.
No problem.
The robo-ception, I presume, is on your...
Are we having one today?
Oh, I don't know. If not,
It's totally, the students run it, they don't tell us anything, so it's totally random. I don't think I've heard anything.
Robo session? What is that? That's on a Friday?
robo-ception, they do...
Oh, Roboception.
Large parties.
Cool.
Okay, let's get started. It's my great pleasure to introduce today Greg Sawicki, my colleague and old friend to the Robotics Institute. Greg went to my alma mater for his undergraduate degree at Cornell University. He did his master's work at UC Davis, where he authored a controversial paper with Mont Hubbard on the question of whether it's easier to hit a fastball or a curveball for a home run. Answer, curveball. This did not sit well with some baseball aficionados. After that, Greg joined the graduate program at the University of Michigan, where we met. And without Greg's help, I never would have finished my dissertation. We had a session that we called Doc Stock, where we met at the coffee shop every day and just sat there and pounded it out together. Greg's a great guy to talk science with. He's always interested in talking about exoskeletons and robots under any conditions. Tonight, we're going to be going to a place called the Butter Joint. If you are an exoskeleton aficionado or robotic prosthesis person, please, I invite you to join us at 7 o'clock, 7, 8 o'clock. For the last, 5 years now, Greg has been a professor at North Carolina State University. He also did a postdoc with Tom Roberts, a renowned muscle physiologist. And he's going to tell us today about some of his exciting recent work in exoskeletons. So,
Thank you. Whoa. Okay, I don't have to say anything now. It's over. Thanks for the intro, Steve. And so what I'm going to tell you about today is I'm going to start off with, it's actually a 5-year-long project that's kind of just culminating in the last couple of weeks that Steve's been a primary player in. So I'm happy to present that here at his home institution. And then I'll follow that up with some of the more detailed, basic, fundamental questions that we addressed in my lab about what happens to underlying muscle dynamics when you attach either springs or motors in parallel with the biological muscle-tendon unit system. Okay, so start out just to say that humans get pretty good gas mileage for the task that gets us around, locomotion. We're among the best. We can build robots that match humans, which tend to be nearly conservative systems. So these use springs and passive mechanisms to behave like humans. So this gives us a clue that humans probably have evolved, not probably, they have evolved over long time scales, and even within ontogeny over our growth after birth, we're able to learn motor coordination patterns to utilize our structure to move relatively efficiently for the task that we call locomotion. And the most efficient way to go is to walk. Just to compare us to other machines that we can build that also move us around the world in terms of cost of transport. Humans are kind of a middle-of-the-road animal. So flying machines we're better than, but there are lots of engineered structures that humans themselves have developed that are more efficient than us to move from point A to point B. Which is kind of surprising given that theory says locomotion should be free, at least on level ground at constant speed. So there are numerous examples. Here's a model from Mario Gomez and Andy Ruina in 2011, and your own Hartmut Geyer has shown also in simple springy models that if you give some initial energy, either through setting a configuration on a stretch spring or some initial velocity or potential energy, that a machine with or a walking model with no losses can theoretically go forever. So there's nothing special about the walking motion or task that makes it necessary for energy consumption to have to happen to move us through the world. So if we think about those things, a challenge comes up. We know that theoretically we should be able to move from point A to point B without using energy, but we do. So that leaves an opportunity. And the way I'll pose it is, can we actually reduce the metabolic cost of human walking by any means, really? What we're going to focus on today is by attaching structures to the body that may be able to transfer energy in ways that sidestep some of the inefficiencies that are inherent in our musculoskeletal system. So the kind of central question that I want to get at, which I'll show an applied solution for at the beginning of the talk, and then kind of get into the details of whether we're at a fundamental limit yet or not, and as far as I think where we are at the end of the talk. So the challenge here is, so this is a cost of transport curve across locomotion speed for humans. On the bottom here you see efficiency, which you can think of kind of like the inverse of cost of transport. So if your cost of transport is low, you're moving with high efficiency. You could see here that for walking, which is the lower speeds on the left, there's a bowl-shaped relationship that humans have. So we get the best cost of transport at intermediate speeds. That's right around 1.25 meters per second for humans. So I'm going to focus the first part of the talk on that, because we want to up the challenge on ourselves. We're going to pick the most efficient movement, lowest cost of transfer movement, and try to make it better by attaching things to the human. So exoskeletons. So you guys are all familiar with Iron Man. Iron Man is sort of the fictional exoskeleton that some of us strive towards. I'm more into the passive approach than the active approach, but I do think this thing's pretty cool. The idea of an exoskeleton is that you use motors or some structures in parallel with the musculoskeletal system it's attached to doesn't even have to be rigid. There's a lot of soft robotics work going on these days also. But the idea is that you have some parallel mechanical element that can help to reduce the effort of the underlying musculoskeletal system. So take some of the load off the biology. And we actually have real machines that look somewhat like Iron Man that are out there. This one here is a Japanese exoskeleton called HAL. It's pretty cool. It uses muscle signals from the underlying user to command torques at the joints. Here is Bleek's. This is now sort of turned into Exobionics, which some of you may have heard of. The original exoskeleton was designed to kind of transmit load in a backpack to the ground through a ghost walking structure that follows you around and stays out of the way. And then this last example here is sort of I would call it kind of the most successful exoskeleton to date. This is an ankle-centric device developed by Hugh Herr's group at MIT that provides ankle plantar flexion, which is sort of that's the functional aspect of walking that we're going to focus on today as well. So despite all this great technology, there's still no published report out there of a portable device that can reduce metabolic energy costs below normal for normal walking conditions. So not for, we kind of term things cheating if you add an additional demand and then try to cancel it. We think of load carriage as that situation, going uphill, forcing people to walk at speeds faster than they would normally choose, for example. So that challenge is out there still. We have not found ways to, within the task of human locomotion and specifically walking for the talk today, to add things to a person and reduce their cost. Why is this? I think largely because of the fact that you're required to add some mass to a person in order to support the loads that you want to transfer to them. And carrying around mass is expensive. And generally, engineers who are good at controls and actuation, they're controls and actuation happy in some sense, you could say. The intuitive solution is to place bulky actuators on a frame and use a brute power solution to try and cancel out the effects of added mass. And so far, that hasn't worked very well. Here is a theory that's been posed also by Hugh Herr's group that suggests that there is a single metric called the augmentation factor that should be a good predictor of whether or not you can get a metabolic improvement when you walk with an exoskeleton. Just to give you a sense for the legend on this, tethered solutions don't count in our challenge because we're stealing energy from the wall, and that means you can't be portable. Untethered portable solutions all increase the metabolic cost, so the metabolic improvement is negative. And there is this one example, the ankle exoskeleton that I just showed on the previous slide, that's been able to break the normal barrier for load carriage, which is a pretty huge achievement. It's a nice achievement, but again, we don't count the added mechanical demand in the baseline challenge because you're making it harder, and then you're creating a challenge that then you're canceling out essentially. So we want to up the challenge, and we want to reduce the metabolic cost of normal walking, but not use any external energy source. So now we're going to go for a purely passive solution and see if this is possible. So that was sort of the baseline challenge that maybe 5, longer than that. I would say going back to graduate school days in the exoskeleton labs around Michigan, this was sort of like a lofty goal. Could we actually reduce energy cost? And we started out with tethered devices. We did pretty well. And as time went on, the challenge became up and up and up. And so this is where we are now. And in my lab, what we try to do is take some inspiration from the biological system. So we do a lot of basic science of human locomotion, which I'm going to spend just a few slides on here, because these provided some of the motivation for the design that I'm going to share with you in the next few slides. So maybe people here are familiar with the standard gait assessment kit that you see in locomotion labs. We've got a split belt instrumented treadmill here, so we can measure ground forces. Standard motion capture. Combining those two things lets us use inverse dynamics to try to estimate how much power muscles are producing at different joints across the lower limb. We can use electromyography to see what muscles are on when. And sort of a new tool that we've brought into my lab in the last few years is ultrasound imaging, where we can get real-time images of how muscle fascicles are moving under the skin. And in particular the calf muscles. So we can separate out the contribution to a joint power output from elastic tissues, or between elastic tissues and actually muscle shortening, which is important because you can kind of understand a little bit more about how the biological actuator is managing energy. So a postdoc in the lab, Dom Ferris, who's now moved on to Australia, set out to answer 2 pretty simple questions. Number 1 is, how do humans distribute power output amongst their lower limb joints? This is an important question because if you're trying to make the decision of where to place your exoskeleton, one intuitive way to do this might be to place it where the highest energy demand is in the first place. And we can use inverse dynamics to figure that out. We can calculate across the lower limb, if you sum up the power being generated by muscle tendon units around each of the 3 joints and partition those, you could see where the majority of the workload is done. The second question was, if you zoom inside, in particular the ankle joint, because that's where we can make clean ultrasound measurements, can you partition that energy further into a muscle and tendon contribution? So the power distribution. Before I even show it, I want to take a poll. How many people think that the hip joint is the major power source for walking and running? I have a few hands. Knee, ankle joint. You guys saw my title slide. It's like, okay, he's motivating this title slide that he already revealed. It's true. It turns out to be across the board, ankle on average is the major player. So you can see these pie charts that we use here. Black ankle, gray is knee, and white is hip. And this is just the positive energy developed by the muscle tendon units across those joints over 1 gait cycle for walking on the top and running on the bottom. At the most efficient gait, or the gait with the lowest cost to transport, ankle's it's nearly half of the total power outputs coming from the ankle. So ankle muscle tendons are a major power source. So what about how much of that is muscle versus tendon? Any guesses?
2/3 muscle.
2/3 muscle, okay. Anyone for tendon heavy power output? Okay, so we have this huge elastic structure there, which is the Achilles tendon. Might as well use it, is one hypothesis. Muscles are great, they're motors, might as well use them. That's another hypothesis, right? Turns out that if you do the measurements, so this is what an image looks like. It's pretty hard to see without the lights turned down, but let me try to guide you. This ultrasound probe is about the size of a pack of gum. You can attach it over the muscle belly, kind of like an EMG electrode. And maybe you can see that a little bit better. It's still pretty hard to pick out. I should have put a tracked image on there. So you can look inside, like it's like you're taking a slice. Like if I sliced my leg like a bagel and I peeled the top of the bagel off, and I got a cross section, and you can see fascicles here. I'm looking from left to right. It's oriented just like the graphic over there. Let me play it one more time. Hopefully you should see some pulsatile behavior. So the fascicles are just to the right of that hard white line, which is your skin. And as you move to the right of the image, you're going towards the tibia, looking through the back of the calf.
The skin should be sliding relative to the bone, and in some sense relative to the muscle. And I gather your sensor is fixed on the skin, so it makes sense the skin looks like it's not moving.
I think that's partially true. I also think the resolution of the image probably isn't quite high enough. The contrast between skin and the surface fascicles may not be high enough to see small movements like that.
In some sense, don't we need to correct this image so that it's relative to the insertion, or, you know?
So what we do here is, what we do is we pick out a fascicle that we can see completely within the image. And so if it's moving, it is true that relative movement of the probe relative to the fascicles is an issue that people are working on that we haven't spent much time on. So, you know, this is not an entirely exact measurement. We would need to also, I think, animal studies where we take simultaneous measurements from sonomicrometry and ultrasound would be a good approach to start to dissect how big of a problem this is. But there's other problems too, like projection error. So, right, muscle's three-dimensional, and we're taking a 2D snapshot of it. So.
Well, and also the direction of the fascicle changes as they contract.
It does, and it rotates too. So what we're doing is making a planar approximation. I don't think it's horrible. I mean, we're trying to get a best case, or a best estimate of, in general, how much sharing is going on.
Well, I buy if you can see both ends of the thing, you're all set.
Yeah, so you can, I have, this is a cleaner still image. So what we do is frame by frame, we try to track a single fascicle throughout the movement. And then we can measure its pennation angle, which is this angle right here, the angle of contraction with respect to vertical or some axial direction, and we can measure the length. So you can actually get forces in the fascicles separated out from forces in the tendon due to the geometry and so forth. But there's a lot of estimates happening here that get us a rough idea of what the sharing is between muscle and tendon.
Why not inject some opaque material into the muscle?
Good idea.
Do it with buckshot.
Yeah, no, I think these are all really good comments that, you know, this use of ultrasound is pretty new, I would say, and there's just it's starting to gain traction where image processing folks. I think algorithms too, like sort of image processing algorithms can take care of a lot of this, the tracking problem in particular. All of our data, this data I'm showing is a few years old now, but we tracked it frame by frame. It's time consuming. I'm more confident in it as a result, but at the same time, it's a lot of time.
Manually track it?
Yeah, frame by frame, 50 hertz, 50 to 80 hertz sampling. So it's time consuming. Take home point here though is that it's more like 50-50 for walking at preferred speed. So the Achilles tendon is storing energy early in the stride, and that energy is being returned, and that returned energy is about half of the total energy that comes out of the ankle joint muscle tendon unit structures. It's a little bit more tendon heavy when you go to more bouncy gaits like running, and I'll show you later hopping. Hopping's got like an 80-20 split. So if you hop in place, 80% of the energy that's coming out is tendon recoil, which makes it a nice model system for studying sort of the fundamental questions about what happens when you put a spring in series with people. So if you look at the time course of length change, in black here is the fascicle. And what I'm showing you is over a gait cycle. So at 0% here is when the heel strikes the ground. Then the foot becomes flat. The tendon starts storing energy while the fascicle remains at relatively low velocity. So it's kind of an isometric clutch-like contraction. And then there's a bit of shortening kind of right at the end. So you can see here, there's an initial shortening, relative isometry, and then some shortening at the end. That's where that sort of 50% of work's coming from. Force is coming down, but the muscle's also shortening, so you get some power out of it. The bottom line here, though, is that the velocity over the majority of stance, when the stance limb's on the ground, in this muscle, is near zero. So it's really acting like a rigid strut. And in an engineering sense, that's what a clutch does, right? So it's providing a grab onto the tendon without much length change, like a latch. And then when activation declines, that muscle it's free to do work. It will shorten, okay? And actually there are models. Here's a model by Ken Endo from Hugh Herr's group from a while back that shows that you can generate walking using timings of clutches and springs across pulleys in something that has limb-like geometry. Okay, so this is what inspired the design that Steve and I and my graduate student Bruce Wiggin have been developing over the last 5 years, is this idea of a clutch and spring. A lot of energy happening at the ankle, a lot of power output happening at the ankle. A lot of it is elastic energy storage and return. Why not try to sort of copy paste that system outside on an exoskeletal structure and use a clutch spring that works in parallel with the person's underlying physiology to try to offload that holding function of the muscle and reduce the energetic demands of walking. So we built this thing. Over the course of years, it got to be pretty streamlined. We got it down to about 400 grams, which is about the mass of a pretty lightweight running shoe. It's got a clutch mechanism which is purely based on kinematics. So it's not very versatile. This is designed specifically for 1.25 meters per second steady speed. But the way this works is timing pins engage a ratchet pawl mechanism. It's a unidirectional clutch. So the phases of locomotion, again, going from left to right here. You've got heel strike. Just before heel strike, as the toe is sort of moving towards the shin to prepare your heel for striking, the engagement pin moves the pawl onto the ratchet. Then when your heel strikes, ratcheting occurs to foot flat. That's the direction that's allowed. So you get a little click, 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 click. Once that direction is reversed, as your tibia starts to move over your flat foot, the clutch is now locked. And the person's energy, kinetic and potential, is temporarily dumped into the stretch of a spring that's acting around the ankle joint. And then later, that energy comes back out as the person uses their trailing limb to push off. And another engagement pin comes from the backside, removes the pawl from the ratchet to allow free rotation during swing. And all of this just happens based on kinematic cues that we know are pretty regular for this walking speed on level ground, okay? We have a sort of low-powered version of this that uses an electromechanical switch, which will make it more versatile for faster walking speeds or maybe changes in terrain or a situation where a person might have unknown kinematics and we want to trigger off, say, their muscle activation or a foot switch or something like that. And I could show you videos of that later if you're interested. So here's a picture of what it looks like when somebody walks in it. Just want to remind you that this cable is making a measurement. It's not supplying power. It's a load cell, so we can see how much force is in the spring. It should slow down and zoom in a little bit. So what you could see here is this green extension spring, tension spring. Right now, it's storing energy, giving it back. Heel strike, ratchet, storing energy, giving it back. Disengage, heel strike, foot fat, so on and so forth. And again, this is all just a passive mechanism that's using the kinematic trajectory. We're exploiting a kinematic trajectory that stays relatively invariant to time the engagement and disengagement of the clutch. So, does the stiffness of the device matter? Another question.
Can I interrupt before you move on to the topic here?
Yeah.
This is typical Democratic thinking. We have an election coming up. You're not getting energy from some magic thing that's free. You're taking energy from the forward velocity of the system.
Yep.
and giving it to the ankle.
That's right.
That's not a good idea, you know, because then we just have to raise more money to get forward velocity back.
Well, if you
You
get,
can't tax one guy and give it to the other guy.
if you give most of the taxes back to the people, you're okay.
No, the right taxes. It just doesn't make any sense.
It's not about that monetary system, it turns out. I'll interpret that later at the bar. No, so it's, hopefully after I'm finished, you'll be more convinced that it's a good idea. That's all I'm going to say right now. So does the stiffness matter of that spring?
That figure suggests that it does.
Yes. Okay. So this is a model of a passive dynamic model of walking that, well, it has a hip torque, but it's got a compliance at the ankle. Hip torque's driving the thing, and you can sweep the stiffness of that ankle spring and ask the question, how much energy does the hip torque have to supply? And it turns out that there's an intermediate spring stiffness where things work out that you're not too stiff and you're not too compliant. You can get the lowest cost of transport. So this sort of motivated the idea that you can also just do the thought experiment that if the thing is completely stiff, it should lock up your joint, and that's probably not a good idea. And if the thing is really compliant, you can't store much energy in it. So there should be a sweet spot. So we set out to sort of find where that sweet spot is and see if it exists and where it is. And so Bruce's dissertation was focused on sweeping stiffness and trying to understand how metabolic energy cost depends on the stiffness of that spring that's in parallel with the person. We use some calculations of the quasi-stiffness of the ankle. So if you plot the moment angle curve around the ankle joint, and you calculate the slope during the time when the joint is being loaded, that's what we call quasi-stiffness. This just gives us an idea of where humans are operating. We wanted to attach springs to the human that spanned all the way from sort of 0%, which would be no spring, up until 100% of the quasi-stiffness of the person's own joint, just as a clean way to sort of parameterize the sweep. And that turns out to be about 300 to 400 Newton meters per radian in that time when foot flat, when the Achilles tendon is stretching on a flat foot. So we designed this experiment where we created rotational stiffnesses by using linear springs through a moment arm in a set way. And then we had people train also, because we know learning is important. So people trained for 3 sessions. They got 7 minutes on each spring. So 21 minutes of total training on each spring on a working device. And then on a 4th session where we made some measurements, they walked for an additional 7 minutes, and we collected data in the last 2 minutes. Why did we pick 7, 7, 7, and 7? There's evidence out there that suggests somewhere in the 20 to 30 minute range with devices like this is enough for the person to accommodate. On powered devices that are not this device exactly, but that's what we use to motivate the protocol here. And then we could ask the question, what's the relationship between the stiffness of this device and the metabolic cost of the user? So here's what happened in terms of the mechanics. What I'm showing you here are the functional stages that I've already described. So heel strike, the clutch is already engaged, but it's allowed to ratchet to foot flat. Over this period where the spring is stretching, this is the torque that's developed by the spring in parallel, and you can see that that depends on stiffness. Going at 0, with no exoskeleton, obviously there's no assistance torque. And as you increase the stiffness from relatively low to relatively high, so this is about 30 to 100% of the person's normal ankle joint quasi-stiffness, you get these higher and higher peaks to a point. And this is just showing that the ankle joint angle remains relatively invariant across these conditions, except for the stiffest springs where it's difficult to sort of work yourself into it, right? It becomes harder to steal energy for stiffer springs, I guess is one way to think about it. Okay. For the intermediate stiffness spring, we could get around 0.12 Newton meters per kilogram on average, and that reduced, just to give you a sense, we would reduce the biological moment by about 25%. This is all just by exchanging energy into and out of the spring. And so here's the sort of the big, pretty exciting result, which is that we could actually reduce the metabolic cost of walking below walking in just normal sneakers by about 7% when we got the spring stiffness dialed in pretty well. And that was an intermediate value at 180 newtons per meter, newton meters per radian. Just to give you a reference, a 7% reduction is kind of like taking off a backpack of around 5 kilograms. So it's not insignificant. It would be like not having to spend the extra energy to carry around your rucksack day to day. If you keep your books with you, I guess that is. So this is great, but why? Why is this happening? What's going on? Is this because we're reducing the work that the muscle fascicles have to do in the calf muscle Achilles tendon complex? Does it have to do more with force? Is it about muscle activations? This is what I kind of want to start to get into a little bit in the next part of the talk. So I'm going to turn our attention now to sort of musculoskeletal modeling work that's been done on locomotion that gives us a muscle level look at how energy is consumed during walking. And this data right here is from a forward dynamic simulation, although it's more like a constrained inverse dynamic muscle simulation. So they take experimental data and optimize a forward model that has lots of muscles in it to behave like the experiment. And when they're done with the optimization, they have some confidence that what the muscles are doing in that model must be like what the muscles are doing in the person who was generating the walking pattern. And from that then, these are just hill-type muscle models, you can take the active state of that model, the length and the velocity, and plug it into an energetic cost model derived from experiments in isolated muscle. And you can make estimates of, this is not mechanical, but it's metabolic power of muscle groups over the stride. And what this graph shows, this is work by Brian Umberger. Ankle extensors are the thing I want you to focus on in dark, in the dark solid curve. Then you've got knee extensors, hip extensors, and then the flexors in total, and then the sum of everything. So you can use this pie chart idea to now look at the metabolic energy use rather than the mechanical energy use. And what you find is that the ankle extensors, where we're providing the assistance, are responsible for about 20% of the metabolic energy cost based on this model's estimate. Now, we're reducing if the moment is what's responsible for that cost. This is only one possibility, but just to do a back of the envelope calculation. If you take 25% of 27%, that should give you the amount of metabolic energy that you should, in theory, save. And that comes out right around the 6-7% that we measured, which is nice. And then the other thing I want to point out is that, it might be hard to see here, but here's what the mechanical power profile at the ankle joint looks like. What's really interesting is at the time when the muscles around that joint are spending the most metabolic energy, at the joint level, we see absorption of energy. And I'm going to say right now that my initial exoskeleton designs, these pneumatic actuators, were designed to take care of this. The problem is that's not where the metabolic energy is being spent. The metabolic energy is actually being spent early to hold on to the tendon, and then the energy late is actually, even though there's some muscle work happening there, it's actually quite a bit lower. So the metabolically taxing task in walking, this would suggest, might actually be holding on to tendon and acting like an isometric clutch at high muscle activation. So maybe the reason our device works reasonably well, even though it's passive, is that it's not about trying to replace mechanical power with the device. It's actually about trying to provide body weight support, reduce forces earlier in the stance phase, where the metabolic energy penalty is quite high. And by the way, this metabolic energy doesn't need to be there if there were no calf muscle and we replaced it with a mechanical clutch. It's an inefficiency built into, it's not even built in, it's an inefficiency of the muscle tendon system at the ankle that you shouldn't need metabolic energy to be a clutch. So we're unduly using metabolic energy in our calf muscles to clutch a tendon. And the way this device works is that we provide a parallel pathway in an inert substance, which is just a material that provides some of that holding torque in a spring that's now external to the person. So I don't think that this line, which is about net work, net energy power, about power transfer, is really, that's not a constraint, is what we're showing. And actually, it may be the wrong way to think about exoskeleton design is replacing joint level power output. In fact, if we take a muscle level view of the system, turns out that large amounts of metabolic energy are being spent by muscles that are producing force nearly isometrically during times when the joint's absorbing energy. Okay? So that's kind of a key result, which is that the roadmap that you get from sort of joint level analysis may be misleading when we think about where and how we should attach devices to reduce person's energy cost. Okay, so that's sort of part one. Few conclusions. So basic studies, I think, are important. So we wouldn't have even gotten to the ankle and this elastic mechanism if we didn't sort of see how humans did it in the first place, I think. We can reduce the metabolic costs without actually transferring net energy to the person, and instead by just strategically exchanging energy while offloading, while producing force assistance to and from a person through a device. Streamlining is maybe more effective than multi-joint high-power systems. So very low profile, targeted, specifically to times when muscle level analysis is telling us is the right time to produce assistance. Again, it's not necessary to impart net mechanical power from the device to the user for a metabolic benefit. And we've shown that stiffness matters, but more is not necessarily better. What happens at those high stiffnesses, compensations start to rear their ugly heads. So you get things like increased knee flexion, muscle activation to prevent hyperextension of the knee. You get coactivation of the tibialis anterior muscle. The reason for that is unclear, but it's there in the data. At the center of mass level, you see increased work in the rebound phase with high stiffness springs. This is all kind of secondary data that I don't have time to get into, but would be happy to talk with people about later. Are there questions about part one?
Isn't it troubling that the swing burns so much metabolic energy?
That swing burns
So much metabolic energy, and it's something completely different going on. All the joints are moving, there's none of this isometric clutch stuff.
So your question is not about exoskeletons, but in general, why is it that humans spend so much energy during swing?
So you're putting forward
Let's go to
a
that
view
slide.
of how the system works, that it's clutches and springs.
So you're over here and you're like, what the heck's going on here?
That ain't clutches and springs. And it's, it's not as much as the stand side, but it's, 60%, 70%. Why is it so big? Are you sure?
I'm not sure it's not clutches and springs, Chris. I think if you talk to Art Quo about this, he would argue that there's a high chance that it is clutches and springs. Well, Jesse Dean, others, Quolings.
You guys are vast mafia.
I mean, the cost might be high because muscles are acting isometrically, and isometric contractions actually are pretty expensive. It's expensive to run a muscle like a clutch.
Yeah, okay. What is the comparison of this metabolic cost to just keeping warm?
Oh, I don't know the answer to that.
What's that?
It's about, 100 watts versus 200 watts to walk at this speed.
So you mean the metabolic cost of standing in place is, that's what you're, yeah.
So
It's a little different than keeping warm
if you make
if I'm in bed lying down with blankets on me, but.
if you make this too efficient, they're going to start feeling cold.
Oh man, these are barroom discussions. I want to get to the second part, hopefully, for a little bit at least. Okay. They're good questions, but there's one other important message I want to give before people have to go in 15 minutes, which has to do with more of the detail of what's happening at the muscle level. And we don't know this for walking yet, but we've used vertical hopping as, I think, a nice simple model to start to try to understand how this guy affects the dynamics at the muscle level. So we can come back to our ultrasound measurements and also simple models. And I want to argue that simple models may be a nice way to try to start doing some optimization in the modeling world to figure out exactly can we discover what stiffness is best from simple models, I guess, is kind of the thing I want to encourage people to start thinking about and working on potentially. And what's nice about this is we have some experimental validation for these simple models through ultrasound images. In a task that is very ankle dominant, so this also makes it a nice system. So coming back to pie charts at around 2.5 hertz, which is where the metabolic minimum occurs across frequency, we found. You're up around 60 to 70% now ankle driven. And then if you look at the muscle level, you're nearly 75% of the positive work during vertical hopping is coming from tendon recoil. So we have this system it's still, you could argue, a version of human locomotion, maybe more like running than walking, where the ankle joint muscle tendon units are really central to the task. And then so we can this device actually can be a lot simpler because we don't need a clutch because the posture is always toe down and there's not a time when the person naturally wants to move against the spring, which is the whole reason you need the clutch during forward walking. So we can just attach springs bilaterally in a very simple, and we're not trying to streamline this in any way either. This thing's bulky. We could care less about breaking any records here. Really, we're using this as an experimental tool. Now, in the modeling world, you can think of this vertical hopping system in its simplest form as a ground reaction force acting through a lever system to load a muscle tendon unit, which is a Hill model. So it's got force length, force velocity, activation dynamics in it. We know what these properties are like for humans from lots of literature. And we can just simplify it into small angle approximation. We simplified it into a system of pulleys and masses with a little bit of gravity and a Hill model that's driving the whole thing. And then what's cool is we can put this spring in parallel with the system at any stiffness we like and drive this in a purely feed-forward sense. No experimental data necessary. This is very simple, purely feed-forward. It's truly forward, which means it can be predictive because we don't rely on any experimental data to make the motion happen. Okay, it all starts with muscle activation. So what you get is this thing starts from rest. There's a few accelerative hops. It gets into a steady state. You can perturb it, which is also kind of cool. So I could go in there and kind of smack it and see what the perturbation response is. I like it as a nice simple model to start to understand how that influences that in fundamental locomotion behaviors like acceleration, steady gait, and maybe even perturbation response. So this just shows that the model does things that you would expect. It produces force when it's on the ground. There's a flight phase, so it leaves the ground. The length changes. In blue there is the tendon. In green is the whole muscle tendon unit, and you can see the fascicles are behaving nearly isometrically when the system's on the ground, which is what we expect and what we measure. Velocity is nearly zero. So literally a clutch spring happening again, even in this simple model. Power outputs dominated by series elastic tissues, not very much coming from muscle. This is in the most tuned state. So then we can generate these contours and ask sort of what if questions, right? Parameter sweeps. In this bottom left-hand corner is when the muscle is basically off and there's no exoskeleton in parallel with the system. At the top right corner, I have an exoskeleton that's very stiff, and the person's also activating their muscles maximally. And then I can play in this whole space, right? And I can generate, the way we assess injury risk is by looking at the strain in the muscle part of the model to see if it exceeds a certain threshold, which we know from literature. So you can see here that at the bottom left-hand corner, when you're not turning your muscles on a lot, like basically you're dead to the world, no exoskeleton helping you and no muscle activation, your muscles are going to passively stretch a lot, which induces injury risk. There's a whole region of this space where you never even leave the ground, so we don't care about that either. So basically, we can narrow down this space into a smaller subspace of viable hopping solutions. And this is just the system power output. So this is kind of intuitive too. If you follow me from top left, 100% no exo, down that dotted path, you can follow a contour of constant system power where I'm turning down my muscles and using a stiffer and stiffer exoskeleton to maintain the same overall kind of system power output, right? So this is just saying you can trade off, it's kind of obvious, you can trade off muscle activation for exoskeleton stiffness and still move in the same way. And the loading curves of the whole system are invariant. This turns out to be sort of what humans prefer to do if you study them across lots of different stiffnesses. They seem to maintain an overall force displacement relationship regardless of what you attach to them. So our model can kind of simulate those conditions. Now here's what I really wanted to get at, okay? There's a strange thing that happens when you attach a spring in parallel with a muscle in another spring, okay? That exoskeleton spring is taking some force, which means that the tendon part of the biological system is seeing less force, which means it's going to be at shorter length, which means that the fascicles have to operate on average at longer lengths if the overall kinematics of the movement are not different. So what this suggests is that even though you can reduce force in the muscle tendon unit, the muscle may actually be put into a situation where it has to undergo larger excursions if the total movement pattern doesn't change. And that means in the best case, that means no change in fascicle work. So force is going down, but displacements are going up. But the amount of work being done by the fascicles is not changed because force and length change are trading off. In the worst case, you might actually see an increase in muscle fascicle work during tasks when you're using an exoskeleton, which we know would have a pretty severe metabolic penalty. And I feel like we don't have the evidence yet, but for stiff springs during walking, there may be something like that going on, where we're detuning the underlying physiology to such a degree that we're causing the biological muscle fascicles to have to do more work at metabolic penalty, even though we're reducing the force with the parallel spring. And there's a certain stiffness where that behavior happens that may be responsible for the bowl-shaped nature, partly responsible for the bowl-shaped nature of the metabolic reduction data that I showed you. What's also cool about the simple model is you can look to see where the actuators are in their force length and force velocity curves and how adding springs in parallel might influence that. So you can see here as you go from orange to green, the exoskeleton's taking over more and more of the workload or more and more of the force support. And the muscles they're both going through larger excursions represented by the bar, and they're operating at longer average lengths. This is not a good thing. If we go too far to the right here, we're going to start causing micro damage to the fascicles. And of course, the longer that bar is, the more opportunity for fascicle power output and work, which is metabolically costly. So it's a bit counterintuitive that by actually providing some external mechanical assistance, you may cause the underlying physiology to have to have higher demand on it. Question?
Are the symbols at the average velocity?
Yeah, these are the, I can't remember, yeah, I think these are average, and then this is the range that it goes through. This just means that it's spending more, it's not symmetric, right? Okay, so if we make ultrasound measurements during hopping, we find the same exact thing that the model predicts. So what I'm showing you here is estimated force in the soleus muscle based on inverse dynamics. So S, the solid line, is the spring condition when the exoskeleton's in parallel. The no exo and the no spring conditions, the forces are higher, right? So you put a spring in parallel, forces go down, no surprise. This is crazy though. It's not crazy actually, we kind of expected it from the simple model. But you get a large increase in fascicle length change happening. And when you combine that reduced force with increased length, there's no difference in the mechanical work of the fascicles. Which means that any reduction in metabolic energy, at least in the local sense, can't be coming from reductions in mechanical work of the muscle. It's got to be some other mechanism, and we think that we're more and more confident that this is reductions in force. Again, which guides your exoskeleton design prescription quite differently when you start thinking about force support rather than injecting net energy or using sort of the power roadmap to design things. Here's metabolic rate, so you can use these simple models also to estimate metabolic energy costs. This is another really interesting thing. So what you see here is that the metabolic cost goes down. Okay, the starred conditions are the data we have for humans. But what we know is that for hopping with very stiff springs, metabolic cost eventually goes back up. So how does that happen in this space? One idea, this is one hypothesis that we need to test. Let's say that you operate by the rule, don't hurt myself, stay in the air, and use the least amount of metabolic energy possible. What you're going to do is kind of skirt this line. And at some point, even though you're getting a lot of stiffness support, you have to turn your muscles up in order to complete the task of hopping, to leave the ground. So there's a fundamental constraint that at some point I fall off a cliff, and if I want to keep moving in an exoskeleton that's stiffer and stiffer, I have to turn my muscle activation up. Now that's for the task hopping, defined by an aerial phase. So people could certainly just decide to bounce or something like that. They wouldn't really go anywhere. You certainly can't move forward by bouncing without leaving the ground. It would be tough. So if we extend these models to sort of forward moving, forward walk, forward locomotion cases, that's basically a future direction that we want to go in. And then, okay. So other modeling approach, which I'm less excited about, but I think is important to show. This is an OpenSim based musculoskeletal model. So it's got slightly more complex morphology. I've got individual muscles in there. I'm not lumping all the muscles together. And if I wanted to, I could generate a model like this that has a whole leg. What we did is we used measured joint torques to move the knee and hip. And then we focused on asking the inverse question about the ankle muscles only. But what I want to stress about this is that it needs experimental data, which means I can't make a prediction of what's going to happen in a condition with an exoskeleton that has some other spring that I don't have data for. So just throwing caution to the wind. These models are nice. They certainly give an individual muscle idea of what might be going on, but they're only interesting in the sense that they could tell us about the basic questions about what's happening in muscles. They're not interesting at all for, at least not yet, for telling us what happens in a situation that we don't have data to constrain the model with. So a challenge to the group here is we need models that have this anatomical complexity and detail that are truly forward, meaning that I can change the parameters of a device that might be attached to it and let it go and be confident that it's going to make a reasonable prediction about what the human would have done in that situation. Another version of a data-driven model here, which is, again, throwing caution to the wind. Simple is better because it's forward and we can make predictions, but we need more complicated musculoskeletal models that are truly forward. Okay, so I already said that. I already said that. Models and experiments all agree when you put a spring in parallel with a compliant muscle tendon unit, you cause it in the worst case to do more work. In the best case, you don't do anything to the work of the underlying fascicles. What this means is that metabolic energy reductions that you might observe are probably not coming from changes in muscle fascicle work. It's all about supporting force. For this particular joint and this particular muscle tendon unit, I want to qualify. And then finally, again, joint level mechanical power may be a really poor guide for allocating exoskeleton assistance. We need muscle level approaches. Okay. Final thing. You can take this simple model and you can put it into a muscle ergometer and you can attach a real muscle to it. So basically what I'm simulating a dynamic environment that's completely up to me. It can have a virtual spring in it, a virtual exoskeleton. I could do things like change the lever relationships between the input and output pulleys of the task and so forth. But what's cool about this is I can make direct measurements on a real muscle. We use frog muscles, so this is a scaled down benchtop approach. And actually observe what's happening at the muscle level, and hopefully down the line make energetic measurements on this prep too, so that we can actually not have to depend on model estimates and start to understand fundamentally how all these things play well together. Okay, so that's all I have. Thanks for listening. I'm not going to read all these, but this work's been supported by lots of people, so thank you to them, and thanks for listening.
So your diagrams and sketches are for stone wall floors and bare feet, and your videos are for bouncy, dissipative floors and $400 shoes.
Yeah.
And the agreement between model and experiment seems like it should not be quite so good.
I'm not sure it's quite so good. I mean, if you look carefully at it, the qualitative ideas are certainly represented in both. But the devil's in the details. So small changes in 10% in the velocity of a fascicle can have a huge effect on force production, right? That's a nonlinear relationship. So I don't know. I didn't mean to claim that these simple models are so good that we don't need anything else.
Isn't it true that tendons have mass and oscillations in the tendon-muscle interface burn energy from the muscle like it's going?
Yeah, I mean, we're not modeling hysteresis of any, yeah,
so
sure.
damping is really, really important.
I don't think that's the first question that our lab was interested in. I think you're right, though, and it goes to this other question is, where do you add the complexity next? So, Chris, if you were to take my model and make it and improve it, you would put damping in multiple places?
I think damping is treated unfairly. I think it's far more important than compliance. At least in the robots we build, it's much more important to get rid of oscillations than it is to save energy.
As you mentioned, oscillations at the muscle tendon interface burn a lot of energy.
Yeah. If you give an opportunity for the active myosin to do their thing, they'll do it, and they'll burn energy doing it.
It's sort of a high-level way to try to understand why does it appear to be the case that we can do better than the person. We can add an artificial thing on and make them walk better. So is it a reasonable hypothesis to say that, well, the parameters of the passive elements in the human leg are maybe are optimized for running performance. And if we tried to do a similar thing for running, maybe we would fail.
No, I think
but
humans
because-
are not as good as they could be for this muscle group at any locomotion task. There's no reason to have muscles there doing the clutching. It's inherently inefficient.
But there is this intellectual problem that we're supposed to be optimal from an evolutionary point of view.
There's not one term in that objective function, I guess, is one way to think about it, right? So energetic cost is just one thing. The reason we have muscles there is probably because we don't always walk at steady speed on level ground. But for that task and that structure, there's an inherent inefficiency that we're sidestepping by using an engineered structure to allow a path for force.
So you expect a similar improvement as possible for running?
Yeah, I think so. Well, the caveat being that the added mass problem is a little bit more difficult for running because, angular accelerations are faster and so forth, and distal mass gets to be a real bear when you increase, I alpha, right? Torque is I alpha, so.
Don't we know the answer for running already from the springy track stuff?
No, because that's a series spring. And I think that's a fundamentally different question. So you can't offload a muscle through a parallel force element by having a squishy thing in series with you. All you can do is change the time course that the muscle feels force.
But you can store and restore energy more efficiently. If our springs are, say, 60% efficient, and we give you a 90% efficient spring in series, you'll just shut off your muscles and be as rigid as possible.
It's possible. But I mean, so the springy track, I think that was a 1% reduction or something like that. Yeah. So, maybe that's optimizable. But I do feel like there's room there to play.
You're talking about the atomic man thing?
Yeah, whatever. All
I
that
think
stuff
that was just
Whatever.
Harvard made that up to intimidate their track competition.
Okay, fine.
I don't count that.
No, I think the idea of putting something in series. I mean, if you think about it.
Ads for shoes with springs in them, and like Sharp Rims got a lot of
Yeah, they don't. I mean, there's no evidence suggesting that works. But there is this thing called cost of cushioning that Roger Crom's group's that's put out there, which is that there may be some. This is damping. That damping may be costly for some reason, and if you do the damping with a shoe, you may be able to save small amounts of energy if you tune the shoe appropriately. But the mechanisms for that we don't really know why that works.
So, top secret designers of hydraulic robots are asking the question, how can we use pressure to push hydraulic oil around so to move it forces from one joint to another to make our robots more efficient, which is in some sense a version of this thing. It's just no springs are involved.
Yeah. Chris?
So I'd like to go after politics once again.
Oh.
You're standing up there advocating bipedal exceptionalism. And somehow having flat feet makes us special. And I'm sitting here thinking, what about cats and dogs and cows and pigs and lions and tigers who don't have really an extensive flat foot, don't have heel strike, don't have toe off? Presumably the ankle joint doesn't play a special role for them because you don't exert torque on the ground. Displacements have to be allocated across ankle, knee, and hip. So
Those animals also, interestingly, hardly have any calf musculature.
okay, so are you really saying that we're so different from quadrupeds?
Yeah, I think so.
Doesn't that disturb you?
No.
Aren't they just as efficient as we are?
But I think the same kinds of designs could be applied to quadrupedal legs, just with slightly different morphologies. You wouldn't be offloading the same.
There's
muscle.
nothing there to be offloaded distally in quadrupeds, or there's less to be offloaded. But that doesn't mean there isn't inefficiency somewhere else. There is.
But the only
We
thing
can get
you
it.
do with with the quadruped leg, it's basically the springy leg that Hartman has been pushing. You know, there's no ratchet, Paul, blah, blah. You just, set of compliance.
No,
that's
but
all
you still need the clutch, because you gotta get out of the way during swing, right? The cat, you've seen a kitty cat walk. They pick up their foot and then move forward and then stick it out and then spring lock, right? During that
this
swing, that
model-
cute little swing phase. needs,
This model just doesn't address swing at all. You know, you guys sort of treat it as a black hole. Good things happen in stance and then whoosh, swing happens.
Yeah, I mean, the loads are low during swing too. So
Metabolic
yeah.
power is at least 50%.
I know, yeah. You know, I hadn't zoned in on that. You're right. I don't usually look at that part of the curve.
Wasn't it around like 100 watts?
But-
Huh? It was around 100 watts, like normal resting rate that we human thing.
I mean, if you're going to say that, you know, in
Where
order to
is that?
stay warm, you know, we got to do our thing with our muscles, I agree with that. I don't think the system wants to be efficient. If we wanted to be efficient, we'd have a bottom temperature of 80 degrees.
Chris, you need to preserve your energy so that you can go fight somebody for food.
Why do we have a body temperature of 98 degrees? I'm sitting here burning energy like it's going out of style. I had to look at what I had to do just to fuel this talk.
And you know, 80% of that 100 watts goes into making hot air, Chris.
Oh.
As you know, I'm interested in inflatable robots.
Yeah, I don't think that energetic cost is the only thing. That's all I'm going to say.
May I just say, so I want to take a slightly different stance on something that you answered earlier, which is like, have we beat evolution? I think the answer is yes.
We have in this in the context of this particular task.
There
Yes.
are very few ways in which
We beat it
Or is cheating.
What's that?
There are very few ways in which the device is cheating. Like it doesn't heal itself.
Oh yeah, well.
Things like that. So it's not made of tissues that can fix themselves and stuff. But otherwise, I think this is
So it can't
feasible.
self-adapt, but we can change the design. Right? Yeah. So okay. It's not.
It's feasible.
Oh yeah, it seems that when your clutch engages, it's a transition from DNS to SLS.
Yeah, it's right around there. Yeah.
It seems that most of the energy or the power is already being consumed by that time. The peak is at the end of the W.
Are you looking at? I'm focusing on the AE, the solid black part of the total cost.
Yeah.
And you're saying that most of the energy is already consumed when the clutch engages, when the clutch locks?
I'm focused on the total cost.
Total cost. So you've got hip extensors doing their thing.
Exactly.
So I agree that hip is it's ripe fruit for the taking. But I don't necessarily think, well, I don't know if a spring's the right way to go there. I think you could do pretty well there with actuation
So this,
for lots of reasons.
This
But
is one where Jesse Dean and his students, so he's been working on this for a long time.
Yeah.
Putting springs in between your legs to try to assist with swing.
yeah,
And so people are trying to do this now. Oddly enough, when I think it's Chalangrooks and Dean did this, they put springy exo on the hips. It actually increased the metabolic rate when you put the springs on. And so why did that happen? Because it's complicated. What happens at the muscle fascicle level when you add these to
well, it's not just the local response either. I mean, there's compensations across the whole limb. And we don't know a lot about that. I mean, what we do know is in our own device, when it's not working well, it's because of things happening in other places it's mostly because of things that are happening in other places that are not local to the assistant. So, And it's not necessarily all a muscle level explanation either. It could be that the overall movement pattern is different, or there's some other constraint that has to do with hip extensors that when you attach something to it, needs to be, it's a critical task that keeps us from falling over that something else then has to do. I don't, you know.
Okay, so the real question, you're designing something that's supposed to optimize energy consumption for what people would expect to fall into for long-term, long-distance walking. If people in your lab are going for a hike, would they actually want to be wearing this device?
Well, what would you? You're not in my lab, but that's okay.
Well,
people in my lab, I think, would. So it's another fundamental basic science question. Like, is the benefit from this enough to make people change their behavior? Good question. Steve's lab's thinking some about these sorts of things. Like if you put heavy shoes on people, so if you think of the other extreme, instead you create a penalty. How less likely are people to walk if you give them a small penalty? And so this is sort of the inverse of that. If you give them a small advantage, do they walk more or less? Are they actually willing to take the device and put it on? Probably not in its current form factor, I would say. You know, we haven't spent a lot of time thinking about getting it under a pant leg or what it might look like if it were like actually being used by lots of people. But
It's also out of their control.
what's that?
It's out of their control.
Yeah. We have a clutch that could put it a little bit more in their control, but it's still sort of a state-based. Where is it? So here's it's just a modified ratchet pawl where there's a servo motor on a central axis that turns a gear and moves the ratchets onto an outer, or moves the pawls onto an outer ratchet. And what's cool about this is that's a little foot switch, like a pressure sensor. So you could have that embedded in a heel, or you could hook up to a person's EMG activity, for example, and when their calf fires, you could engage the clutch that's in parallel, or you could let them decide when they want to turn it on by a button press, or you could have, right, it's an electrical trigger. So is that what you were getting at by having no control? I mean, this still isn't full control, maybe the way you're thinking of it, but.
Well, for some reason they wanted to stop going forward. This thing is going to basically, still be pushing them off. If they wanted to kill push-off, for example, dump all the energy, they can do that with their muscle. They can't do it with this thing.
Yeah, that's true. For that one step, yeah.
Are you asking your subjects to minimize their metabolic cost?
We don't ask them to do anything except try to walk normally.
So, I mean, couldn't you say that maybe if you were to ask them to minimize their metabolic costs, that they could do better without the clutch?
What's your name?
Zach.
Zach, do you want to come work in my lab? I think that the field in general is starting to catch on to this idea of using some kind of optimal learning in conjunction with devices that may give advantage to find even better solutions. So, for example, could I get the stiffer springs to perform better if I showed people their kinematics and asked them to match a profile that I knew was going to let them store more energy? Or if I gave them the simple instruction, the goal of this device is to reduce your energy cost. Relax when you use it. Would that work? I don't know. Good question. These are good questions. I can tell you that Jesse Dean's lab showed that if you ask people, this is a little bit different, but just by instruction, you can get people to reduce their metabolic costs when they walk downhill. Because they take a naturally conservative approach to it. So they walk downhill by taking shorter, maybe more stable, maybe they're protecting their tendons from getting stretched too much, who knows. But when you ask them to relax and just let it roll, their metabolic cost goes down by 10% on a downhill slope. So I think that challenge is, I don't know if that's possible on level ground. I think people are not, they're not taking a conservative approach probably. But yeah, that's a great idea. I think that self-discovery of, or giving the person a way to be in the loop is could be important.